Okay, sound looks good. Yeah. All right, so welcome. So review session. I guess this is a review session. But what I'm going to do is I have like all the sections laid out, and I just want to go through each individual section on the exam, and then we'll just talk about. I'll hit like whatever I think is important for those sections, and we'll talk about it. So let's jump right into it. So first things first, let me calibrate my screen because I was having problems with that earlier. So this will take 10 seconds. Cool. So, all right. I'm not going to talk about logistics of the exam. You guys probably have heard of that. Enough of that already. Let's jump in. 100%. Good, good. All right. We're going to start off with 4.6, which is on basis. Technically, not on the exam, but you kind of need to know it to do anything on the exam. So let's talk about it. So let's say a set of vectors. Let's say B is a basis for a vector space V if 1, all vectors in B are linearly independent, and 2, B spans V. All right, so this is just a classic definition of what it means to be a basis. You need to be linearly independent, you need a span. Let's talk about the standard basis. Okay, my pen is like running out of battery. That's the other thing. Let's hope I have a battery to replace it. Okay. We're good. Cool. So B spans V. Okay. So where were we? Oh, we're talking about standard basis, right? Okay, so what's the standard basis? So examples then Rn you would have like 1, 0, 0, and these are all dots, and then 0, 1, 0, and then all the way down to 0, 0, 1. Okay. And how many of these would you have? Well, you would have n of these. So that means the dimension of Rn is going to be n. All right, what else? So you have then like Pn, or that's the wrong place to put the n, which is the polynomials, which so you have 1x, x squared, all the way up to x to the n. That would be your standard basis. And how many vectors are in here, or linearly independent? N plus 1. So that's the dimension. And then M and R. So these are the n by n real matrices. So you have 1, and then everything else is 0. And then you got 0, 1, and then everything else is 0. And then you go all the way over to 1 in the bottom right. And the dimension of this is n squared because you move that 1 around everywhere. Okay. And then let's just define what dimension is. The dimension of a vector space is the number of vectors in any basis of the vector space. Okay. And then the last thing there's a theorem which said if you have n linearly independent vectors in an n-dimensional vector space, then 1, they span the vector space, and 2, they form a basis for the vector space. Okay, any questions about bases? All right. For 7, we kind of skipped around this chapter and came back, but this is the change of basis. And this is really a plug and chug section. So you have bases B and C of the same vector space. And then PBC, which you can write as this PB2C with an arrow pointing there. Just seems easier to do it this way. This is, how do you find this? You just put your basis elements B on the left, you put your basis elements C, or you put your basis B on the right, you put your basis C on the left, and then you reduce until you get the identity matrix, and then on the right-hand side you'll have that change of basis matrix. Okay, and another note then is that PBC times PCB is equal to the identity matrix. So what does that mean? That means that if you have one of them, you have the other one just by finding the inverse, right? So if you need to go from B to C, but you have PCB, just take the inverse of it.
Wait, can you talk about that equation? That's like PCB equals BB, C equals...
That's in another section.
That's not for 7.
That's not for 7. This is just straight up change of basis.
What's that?
That's
6-5.
Yeah. Okay. Any questions about just change of basis in general? Okay. So now row space, column space. What do we really care? Row space and column space, we care about AX equals B, right? And for A, we're going to have an n by n matrix. All right, and then we have X, which is n by 1. And then we have B, which is m by 1. Okay, the column space is the span of the columns of A it's a subspace of R M, and that's because each column has M entries in it. And if B is inside call space A, then AX equals B is consistent, which means you can solve this system for an X. So there is some X that solves this system of equations, as long as B is in call space A. Okay, and you note that, okay, so for column space, right, we're talking about B and we're talking about the columns, all right? All right, here's an important fact to remember. The dimension of the column space, I'm just going to write CA for column space, is equal to the rank of A. Okay, so I think I definitely mentioned this in recitation. I think I started in recitation as well. And this one's less important, but it's also the dimension of the row space of A. But really, that first equality is what you really care about. Okay. Finding column space of A. Step 1, row reduce to expose the pivots. And step 2, take the pivot columns from the original not reduced matrix. All right, and you may be asked to go backwards. So you can be asked to find A given column space of A. I mean, for any of these problems, you may be asked to go backwards, like change of basis, right? If you want, if they give you PBC, they might ask what PCB is. Take the inverse. But here you can be asked to find A given the column space of A. I think you guys did some homework problems on this that we did not grade. So I don't think those will be helpful. But in general, does anyone have any idea how to do this? It's not bad, yeah.
We already know however many, like whatever's in column space is literally already in the original matrix A.
Yeah, right.
I don't know how to do it with the free columns.
You can. What can you do with the free columns? Yeah, okay, so you can make them dependent on whatever your column space is, or you can just make them a bunch of zeros.
Yeah.
Okay, so shouldn't be hard. Okay, any questions? That's all I have for column space. All right. 4-9, rank nullity. So A is m by n, and the rank nullity theorem tells us then rank A plus nullity A is equal to n. Where nullity is the dimension of the null space of A. Okay, what's an application? It's the solution, well, it's the complete solution. Complete solution to AX equals B. So if you remember, X is equal to some particular plus some homogeneous, where the homogeneous is the solutions to AX equals 0, which is the null space, right? So it's a basis for the null space. And then XP is any solution to AX equals B. Yeah.
The XH term appears. It's not. It's not.
Oh.
Or so, oh, it's.
Any other questions? Yeah.
Is there like a specific word for that?
It's the homogeneous.
No, not the homogeneous one, XP.
It's a particular solution. That's why it's called P. Yeah. So you can say a particular solution to AX equals B. Good. This is how we structure solutions to differential equations. So we introduce it here. Yeah.
Are we going to like on the test know like or set something up with like XP and XH?
I mean, yeah. If the question asks you to do that. Yeah.
Sure.
What do you mean it's an application of the Rank-nullity theorem? Like, why does this have to do with the Rank-nullity theorem?
It just gets introduced here. Essentially, you see that the the homogeneous system, like you find like the nullity, right? So you know how many vectors need to be in your null space.
Oh.
Right,
Okay.
and it's really, you could have introduced it earlier, but it just gets lumped here. So. Any other questions? All right, I think that's it for 4.9. So 4.10, I'm not going to cover it. It's just a bunch of like equivalent conditions for invertibility. If we have time at the end, I'll talk about it, but I didn't have time last recitation. So let's talk about linear transformations then. So 6.1 through 6.5.
Wait, and the dimension of the null space is always going to equal the dimension of the particular solution?
No.
No.
Right. Those are separate.
So how do you add them? Oh, I guess you could just add
No,
them.
it's just they're just
Yeah,
vectors.
okay.
Okay. Yeah. I mean, we did an example in class. So. Okay. We're on linear transformations. I need to go to the right section of my notes. So linear transformations. The first thing you want to know is to prove a map from T, V to W is a linear transformation, or is not. So first thing you need to show is closed under addition. So how do we do that? We take little v1, little v2 in big V, and we want to show that T of v1 plus v2 is equal to T of v1 plus T of v2. And the second thing is to show that it's closed under scalar mult. So we take K in R, and we take V in big V, and we want to show that T of KV is equal to K times T of V. Look familiar? All right, this next one is what people really freak out about. It's the matrix of linear transformations. So I spent the bulk of the review sessions and I think the past week just talking about these. So let's just give then the high level overview of what's going on. Okay. Bless you. So we have type 1. So there are 3 types of problems. Type 1 is you're given a map T that sends V to W, and you assume the standard basis, or they're given to you. And we're going to assume that V has dimension n and W has dimension m. So then the matrix representation of T is m by n. Okay, we need to give a name for the input basis. So say the input basis B, right, has B1, B2 through Bn. And since we're doing the standard basis, these guys really are just E1, E2, En. So E's are just your standard basis elements for that vector space. Okay? But I just need to give them a name. Okay? And so now you have T is equal to the matrix where the columns are T of B1, T of B2, all the way to T of Bn. Okay, any questions here? This is, I think I covered this in recitation last week. Okay, so what's really going on? So I came up with this analogy last class. So essentially, you can think of it like this. All right. You have Earth, you have Mars. All right, and so Earth is one vector space, Mars is the other vector space. What's going on is that, so Earth has your standard basis, so we have some basis here, right? Or we can think of it as we have some base, right? We have B, and then on Mars we have some base, right? That we want to go to, right? So these are our standard bases on our 2 planets, and T just launches you from one base to the other base. All right, so this isn't very enlightening right now, but it'll be more enlightening when we get to the other types of problems. Okay, so just keep this example in mind for now. Type 2. You have random inputs and that you have their corresponding outputs. So say your inputs are V1, V2, all the way through Vn, and say the outputs are W1, W2 through Wn, right? So each one corresponds to the other one. So you know that V1 gives you W1, and like V2 gives you W2, and so on. Okay, then T of V1 as a vector, right, as a column vector, V2 all the way through Vn is equal to W1, W2 through Wn, and these are all just column vectors. Okay? And that means the matrix of transformation for T is just going to be T of W1 through Wn times V1 through Vn inverse. All right, so your V, the matrix with your V's, they always have to be invertible. Which then brings me to a point where you want to drop duplicate or scalar multiple input-output pairs. So what do I mean by that? So for example, right, if you have T of 1, 1 is equal to 2, T of 2, 3 is equal to 4, but you're also given that T of 5, 5 is equal to 10. Okay. Well, this last guy is just a scalar multiple of the first one. Right? And it's not telling you any new information that you didn't already know. So what we do then, before we perform these steps, is that you just want to like drop that last guy. Okay, any questions? Do we see why we had to drop the last guy here? It's because if we try to make that V matrix, right, and we try to invert it, well, you would have a 2 by 3 matrix, right? So, well, something's up, and it's because we have duplicates. So we just dropped that one, yeah.
Yeah, if one of the matrices were like dependent on the other two, like if you had 3, 4 equals 6, so then would you drop that as well?
Yeah.
Okay.
Yeah. But yeah, you would.
Okay.
But usually it'll be a little more clear.
Okay.
Yeah.
Is that like in this case like B is like it's the like dimension 2 and W is dimension 1?
Yeah. Any other questions? Okay. So type 3. So these are the problems that this is the problem that gives everyone fits. You're given a map V to W. You're given a basis for V, and we'll call it B, which has the elements B1, B2 through Bn. Okay? And now you're given a basis for W, which is called C, which is C1, C2 through Cn. Okay, and now your job is to find, right? You want to find a matrix representation TBC. And before we get to that, I want to make a note. Nothing is preventing us from saying V equals W and or B equals C. Right? So nothing says that V and W have to be different vector spaces. You can be the same vector space, right? And nothing says that B and C have to be different bases, right? If you're in the same vector space, you can have this be the same basis. So I think the problem on the practice questions has this case where V equals W and B equals C, right? Because it's a map within the same vector space and within like the same bases. Okay. So this is the problem. Step 1. It's like type 1. All right, so step 1 is to find TBE. Which is the following. So by the way, oh shit. This should be CM. And the reason is because I want V to be dimension N, and I want W to be dimension M. I guess I also didn't say this is a map from T to W, right? Put that in. Yeah.
How can B equal W if they have different dimensions?
Right, exactly. So V equals, so again, N can equal M, right? You can be within the same vector space, right? So for this to happen, this has to happen first.
And then they would have to have the same.
Yeah. So TBE, right? So this is going to be an M by N matrix. So we have this. All right. In the columns, right, this is why I said it was like type 1, is because you just literally put T of B1, T of B2, T of Bn into the columns. All right, but here in the rows, right, this is going to be your output standard basis. You're going to have E1, E2, all the way through EM. Okay, and the idea is the following. So we're going to go back to this analogy. Okay, so on Earth, you have some base B that you start at, right? And at Mars, you're trying to end up at some basis C. The problem is, by plugging in stuff into B, plugging in B into your map, you can never get to C in the first place. You're going to always end up at some random location, but it's always going to be the same location, which is E. Right? So your map always launches you to Mars, so you're on the right vector space, except you always get launched to this space here, but you want to end up down here. All right? So this is just like a very high level what's going on. So that's what we're doing right now. All right. So by plugging in your b's into T, at least you're in the right vector space. Okay. But you're over here at basis E rather than basis C where you want to be. Does that make sense? And the reason why this is the case is because this map up here, T, like, we had to define it like somehow, right? There has to be some meaning behind T. Like if I told you like T is a function that like sends R2 to R, like, and I give you some like map that does that, that map had to have some intrinsic like meaning behind it, right? And that's because we define this map on the standard basis.
E1, E2, EM, is that like if it's a polynomial, do 1x?
Yeah.
It's like a matrix, you just unravel it.
Yeah. Does this make sense? So this is step 1, right? So how is this different? How is this step 1 different from this step 1 up, this type 1 up here? Well, up here, E is equal to C, so so this basis, like we're done after we get launched there, right? But down here, we're trying to get down here. Right, so we get launched to the right vector space, but we just need to end up at C. Whereas in part 1, all we cared about was just landing on the standard basis vector space up there. Yeah.
What about the given input basis of matrices shows you that you don't get launched into like point B? You get launched into point E instead of point C.
So up here. Wait, can you repeat that?
Like, what about the givens in the problem indicate to you, like, where in the other basis you're getting?
Right. So you're given standard basis in this problem, or you assume standard basis in this problem. So W automatically assumes standard basis, right? And T will always launch you to the standard basis place, right? So down here, right, you just get launched to the standard basis place. In the type 1 problem, that's where we want to end up. In this type 3 problem, we want to end up at basis C instead. So you need to change your basis, right? So that's the next step. Change a basis. PEC in the output space. Right, so once you get launched to Mars, we need to trek down to our base that we want to be at. So from here, we find PEC to get us there. So then, how do we do that? PEC is equal to C, and then you put E, right, and then you reduce. But what is E always going to be? Yeah, E is always going to be standard basis, so what does it look like? Yeah, it's just identity matrix. Yeah.
If, like, for example, like, I don't know, like, E is describing R3. So you have, like, 1, 0, 0, 0, 1, 0,
Okay.
0, 0, 1. How does it, like, translate into, like, each entry of TEB?
So you just put.
Because, like, E1 is, like, 1, 0, 0.
Right. I mean, you just take the first entry in the vector, the second entry in the vector, the third entry in the vector. Yeah. All right, so this is step 2, and then you reduce, and then you need to get I here, you get PCE here, whatever. Or PEC. Ugh.
And that C is from part 1, right?
Yeah, C is given, right?
Oh, C is given.
C is given. We didn't use it for part 1, right? Part 1 we did.
Oh, that equation.
We did these guys, yeah.
Okay.
All right, so step 3, to piece it all together, T BC is equal to PEC times TBE. So you just have to multiply them like this. And again, if you wrote it like this, it'll be easier to see. Right? So you go B to E, and then E to C. Yeah.
So I was confused earlier when you mentioned that if V is W and B is C.
Mhm.
Is that the problem was that you had to show if V is C then V is W? Or
No. It just says that I can give you like
Yeah.
these two could be the same vector space.
so it's a transformation back to itself?
So what happens there is essentially like you're at some basis B on Earth, right? But your rocket's really shitty and it just launches you like down here instead, right? And then you just need to get back
Get there from
there. Yeah.
Okay.
Yeah. So that's what happens. So this would be like TBB, right?
Yeah.
Right. No, this would be TBE, and then you need to find PEB
Okay.
to get back to where you
Okay.
originally were. Right. So I think this is the problem on the practice
Okay.
is you
Yes.
yeah you get sent yourself. Yeah. Okay. Any questions? Let me go back down here. Yeah.
So if you have a basis and you're trying to get from like the standard like basis of the vector space to like the transform version, you use like the P notation.
Yeah, so P is within the same vector space, right? So you notice that we only ever use P like on Earth or like on Mars, right? That's all we did. But T can like launch you to different vector spaces. It can also send you around in the same vector space, right? But you'll notice that T will always send you to your your standard basis.
Okay. And then you need a follow-up step
Right.
to get from like the standard basis of the other vector space
Right.
to
The desired.
basis given.
Yeah, exactly. And so if the basis given was the standard one, you're just done,
Okay.
right? And the other way you can see it is, what if C was the standard basis, right? Then this would also be an identity matrix, right? But then you're just done because all you needed was the identity matrix, right? And then PEC would be the identity matrix, right? Then you're multiplying the identity matrix on the left with TBE. Well, then there was no point in doing these two steps, right?
And then I guess when D equals W then, do you just get like
No. So when V equals W, when V equals W, that just means that this map, we get this map instead, right? Because we're getting launched into the same vector space. So you just get launched into the same vector space. But if V is not equal to W, then you get launched in different vector spaces. Yeah.
For C, for knowing whether C is the standard or not, like we know whether you're getting launched
Yeah.
to the standard standard basis
Right.
based off of whether all the C's are just ones with zeros.
Right.
And whether it looks like a standard basis.
Right. I mean, they'll tell you. They'll either tell you standard basis or they'll give you something that looks like a standard basis.
Which will just be
Right.
a bunch of zeros. And
Yeah.
then-
Okay. Good. Good here. Let's talk about eigenvalues, eigenvectors.
I have a quick question.
Yeah.
Do we have to like, I don't know, like we had those like linear transformation questions with those like actual pictures.
Yeah. I mean, those you just identify a basis and see where they get sent to, right? That was a type 2 type of problem. It's just, instead of giving you like where stuff got sent to, you have to create it yourself based on the picture. All right. I'm going to run a little bit over, but I know no one uses this room, so it's fine. So AV equals lambda V. V are the eigenvectors. They're stretched by A. Lambda are the eigenvalues. It's how much the eigenvector is stretched. Okay, the eigenspace of A, they're all linearly independent eigenvectors associated with every lambda, all right, with every eigenvalue. And then you also have an eigenspace of lambda, which is all linearly independent eigenvectors associated with that particular lambda. Okay. The really important things, the sum of the lambdas is equal to the trace of A, and the product of your lambdas is equal to the determinant of A. All right, and then there was one I introduced on Monday. The multiplicity of lambda equals 0 is greater than or equal to the nullity of A. And this is equal when A is non-defective. Yeah.
The sums being the trace, that's not the same thing as saying like that the eigenvalues are the diagonal though.
No,
Okay.
no.
It just happens to.
No, that only happens when it's a triangular matrix.
Right.
Okay, so for a triangular matrix, the eigenvalues are the diagonal entries. Maybe we can put that one down too. So triangle matrix, lambdas equals diagonal entries. But only for triangular matrices. If you do this for any other problem, we're just gonna give you like 1 point on the problem and not look at the rest of your work, because
What's that word? That.
particular lambda. Yeah. Okay. Finding. Okay. View. Finding eigenvalues, eigenvectors. All right, we're almost at the end here. Step 1. Determinant A minus lambda I is equal to 0. This is the characteristic polynomial. And the lambdas are the roots. Step 2. For each unique lambda, find V such that A minus lambda I V is equal to 0.
Question. question. I know in your videos especially, you kind of like intuitively guess what the V's are.
Yeah.
Am I correct in saying that once you have a number of linearly independent vectors that satisfy that is equal to the amount of lambdas you have,
Yeah.
then you're done?
Yeah.
You can stop?
Yeah.
Okay.
Yeah. We'll touch on that in diagonalization a little bit, which is now. Okay, so diagonalization. We say A is diagonalizable if we can write A is equal to S ds inverse. S is equal to V1, V2, Vn, right, as column vectors. Where V1, V2 through Vn are linearly independent eigenvectors. Okay, D is equal to this lambda 1, lambda 2, lambda n on the diagonal. So the lambdas are your eigenvalues. Okay, remember, these have to be associated with each other, right? So lambda 1 has to be the eigenvalue that you used to find V1. Lambda 2 has to be the eigenvalue that you found V2, and etc. Yeah.
So the lambda or the eigenvalues are always on the diagonal for
Yeah.
your diagonalized matrix.
Yeah.
How is that different from what you were saying earlier about how they're only on the diagonal where it's a triangle?
So this is when you're diagonalizing the matrix, you found the eigenvalues and you found the eigenvectors, right? Up here, what I'm saying is that if you have a triangular matrix like 1, 2, 3, 4, 5, 6, right, and it asks you to find what the eigenvalues are, they're just the diagonal entries.
Oh, okay.
And it's because that one's upper triangular. So up here you didn't know what they were, but down here you already know what the lambdas are. Yeah.
Yeah, it doesn't matter whether it's upper or lower triangle.
Yeah, it just has to be triangular. Yeah, that's why I didn't specify upper or lower, right? So, okay. Almost done. A matrix is defective or non-diagonalizable if for any lambda the nullity of A minus lambda I is less than the multiplicity of lambda. All right, and again, multiplicity is just how many times this lambda shows up. So in other words, number of lin independent eigenvectors associated with lambda is less than the multiplicity. Or in other words, the dimension of the eigenspace associated with lambda is less than the multiplicity. So those three are all the same thing, right? Last thing, applications of diagonalization. One, you can find A given lambdas and V's. Right? You just use A equals SDS inverse. We did that on Monday. And the second application, and the last thing we're going to write, A to the K is equal to S D to the K, S inverse, where d to the k is just, right, so you have like lambda 1 through lambda n to the k, and that's just equal to lambda 1 to the k all the way down to lambda n to the k. All right, any questions? That's everything. Yeah.
So when you're you said that the lambdas and the associated eigenvectors, they have to be like
Yeah, exactly.
those two.
So when you can't do that,
Yeah.
right, then it's defective.
Okay.
Yeah,
Okay,
exactly.
So like if you get multiple eigenvectors from one eigenvalue.
That's fine, right? Because
If you get multiple v's from one lambda.
yeah, you just write the lambda down, right? So you have like lambda equals 3, lambda equals 3,
Oh, okay.
right? That's fine.
Okay.
So multiplicity is just the number of times it's repeated,
Okay.
right? You have to write the number of times they're repeated on the diagonal. But if you have like 3, 3, but you only have one eigenvector for that number 3, then it's defective because you can't pair the second.
If you can't pair one of the eigenvalues to something.
Yeah, exactly. Yeah, exactly. All right. Any other questions?
Yeah.
Oh, scroll down. Yeah.
Is that right?
D equals SAS inverse? Yeah, I think so. You can just work it out this way, right? A equals SD S inverse.
Yeah,
Right?
right now.
Multiply both sides by S. AS is equal to SD. Right? And then multiply both sides by S inverse. And then you get S inverse AS.
So that's right.
No, so this is wrong.
So it's flip.
Yeah, it's S inverse AS.
So just to clarify, if let's say I get like 4 eigenvalues and one of them yields 2 v's and one of them doesn't yield any v.
Let's just do this.
Or like I can
All right? This is my matrix.
Okay,
What are
sure.
my eigenvalues?
3 and 3.
3 and 3, right? Okay. So my D matrix is 3 and 3. Okay. But now if I do lambda is equal to or a minus 3i, right? I get 0, 1, 0, 0. Right? How many eigenvectors can I get? 1. Right? So if I write S, right, 1, 0 is one of them.
Yeah.
Right? What did I put here?
Nothing.
You can't, right? So this is defective.
Okay. Okay. Thank you very much. And you're off sound today, right?
Yeah, 5 to 6, 30?
Here?
Like that? No. 3W8.
3W8.
Yeah.
He was saying something in class. Is it like P inverse P? Is that like he was like saying something that P equals like S inverse? Yeah.
D is equal to S inverse of S.
No, I know, but he was saying like P.
Oh, yeah. I said P C B times P B C is equal to I.
Yeah. No, but he was saying like P in relation to S.
What is
Yeah,
P?
I can
I literally don't know.
I think he was trying
I
to
have
do.
class, but I'm gonna ask about it.
Yeah, I think.
I'll be back.
Yeah, he
I'm trying to prove
he
that.
introduced. Yeah, he introduced this. Right.
Yeah.
Yeah. In the context of diagonalization.
No, Sam, it's so much work this week. This is my busiest week, I think. This
done your office hours.
What? No, I'm moving them. I moved them to 5. I have an exam in like 2 hours. It's physics. So.
Well, I can help you with that.
Probably.
I had a question.
Yeah.
No, you're
I'll
on
answer
51
anything
now.
now.
Practice problems.
Sure.
But I feel like I don't really want to bring it up, but I can just like explain the question.
Yeah.
So
If you tell me what it is, I'll probably remember it.
Oh, it was one of the ones where you had it was like